Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin, and I'm the Technical Director at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speakers, Dr. Jeff Hrivnak and Tony Thornton. Dr. Hrivnak received his degrees in chemical engineering from the Pennsylvania State University and the University of Delaware. Jeff recently joined Micromeritics and brings more than 25 years of industrial experience in the chemical, specialty polymer, and advanced material industries. Throughout his career, Jeff has served on numerous boards and was recently honored for contributions to provide materials for ventilators, face shields, and N95 masks during the early stages of COVID-19. Dr. Hrivnak is currently Vice President of Market Development at Micromeritics. Joining Jeff for this webinar is Tony Thornton. Tony received both undergraduate and graduate degrees from Emory University. Tony is currently Director of Technical Information for Micromeritics, and Tony has more than 40 years of experience in the field of material characterization. His experience included techniques for particle size, porosimetry, physisorption, chemisorption, and picnometry, and has contributed to the development of all of these techniques here at Micromeritics. He is a fellow of ASTM and recently honored with the ASTM Kavanaugh Award for his outstanding leadership and contributions to and the promotion of international standards development. Jeff and Tony, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on characterizing lithium-ion battery separators, pore structure determination.
Thank you, Jeff, for that introduction. Audience, thank you for attending our webinar today. Today we're going to break this webinar into two parts. We're going to first give an overview of the lithium-ion battery market, and then Tony will go into the details of how the autopore can be used to analyze a separator. Since the beginning of the lithium-ion battery industry, Micromeritics has played a very key role in helping research and development develop this technology. Therefore, at this point in the market, we are in every part of the value chain, from raw materials and precursors to the electrodes, separator, and solid electrolyte, as well as the second part of the battery life during recycling. Micromeritics has continued to be a leader because we can help the battery industry improve their safety, improve the energy density, as well as improve the lifetime of the batteries. Measuring certain properties such as density, particle size, porosity, surface area, powder flow, as well as particle interactions. At the bottom part of this slide, we show a wet electrode manufacturing process, and it shows how our instruments can be used at every single stage, from quality assurance to the slurry preparation to coating and drying, and then the final quality assurance. It's not surprising then that now over 80% of the major battery OEMs, as well as auto companies, are utilizing our technology for both R&D and manufacturing. We have 200 current battery customers already, and our year-over-year growth has grown by 3x, which corresponds to the tremendous growth in this industry. Today we're going to talk about separators. So on the right side, it shows a Google Scholar search that shows that over 1,200 papers have been written about Micromeritics separators and lithium-ion batteries and how we can improve those technologies. This is a 50% increase over the last 5 years. Every day in the market, in the news, we hear about how batteries, how automotive companies are trying to move away from the internal combustion engine and move to electric vehicles. From This year, in 2021, going to the next 5 years, we expect 5x growth in the amount of battery demand on a gigawatt-hour basis. This is for a couple reasons. First, you're going to have more electrical vehicles on the road, and then also they're putting bigger batteries in the cars so we can get more mileage. This corresponds to separator demand, and we're going to see very similar type of growth, growing from 5 billion of markets for separators in 2020, going to above 12 billion in 2026. This is about 2.5 times growth, not as much as the battery capacity, but this is expected since you're going to get cheaper prices as you start to develop more of these, which will then help batteries grow even faster as people get lower prices for the battery technology. There are several different types of separators used. You have in the different types of technology. You can either have polyethylene or polypropylene. You have different types of processes, wet and dry process, and then you can either biaxially or uniaxially stretch these. Depending on what combination of these you choose, you have differences in cost, the mechanical performance both in the transverse and mechanical direction, as well as what temperature the separator will shut down the battery at. At the top, you see both the polyethylene wet biaxially stretched and the polypropylene dry unilaterally stretched. Those are the leading technologies right now, but companies are also starting to look at different types of technology like biaxially stretching polypropylene, and they're now moving to technology where you have a tri-layer with polyethylene in the middle, which will shut down at a low temperature, and then polypropylene on the outside of the separator, which holds the mechanical performance so you don't get the electrodes touching and causing a fire. To further enhance safety and thermal stability, ceramic coatings are also being put on all of these different separators. No matter which separator you choose, it's important to measure the porosity, which is a key property. It's important to have enough porosity so you get the lithium ions moving through your separator. If you have too small pores, you're going to get the electrode materials touching and causing a short, which is a safety hazard. So you don't get dendrite formation, which again could be a safety hazard. You need a very uniform current distribution, which is important for the pore structure, uniform pore structure, as well as having a tortuous path through it. And then finally, if you have too much porosity, you're going to have the battery not shut down when you have an overheated battery situation. On the last slide, I talked about how safety is very important for the battery industry. On this slide, I want to highlight a couple of some of the major battery failures that have been in the news over the last couple years. Some of the major names are Boeing, Segway, Samsung, Hyundai, GM, who have had these recalls. The recalls have ranged financially all the way from $200 million on the low end up to $5 billion at the high end. Several of these battery failures, the separator has been a key component for the failure. For example, with the Samsung Galaxy Note 7, the ceramic binder was not adhered correctly, and this was identified as a key contributing factor. And then on the Chevy Bolt, there was a folded separator as well as a torn anode tab, which are manufacturing defects that caused the failure of the Chevy Bolt. The bottom line is safety is very important for the battery industry, and both the research and development, understanding in developing a robust battery, as well as the manufacturing process so you don't get mistakes is critical. And the Micromeritics equipment is a key part of that to make sure you get the proper quality and robust processes. With that, I'm going to hand it over to Tony, who's going to talk about the Autopore and how this can be used to analyze the separator.
So I want to take a few minutes to introduce you to the hardware of the Autopore. We're going to look at software in a bit, but I did want to kind of take you through the features of the Autopore hardware. And basically the Autopore, it's like having two instruments in one cabinet. We have a low pressure system on top and the high pressure system on the bottom. The low pressure system takes care of evacuating air from the sample holder. It does introduce mercury into the sample holder, which we call penetrometers, and then it performs the analysis from subambient pressures up to about 2 to 3 atmospheres, which is user selectable. Once we've finished in the low pressure system, the penetrometer comes out. If you're doing density analyses and porosity determinations, you do want to record the mass after the low pressure analysis, because that's the first time that it has mercury in it that we can determine the mercury mass. And we'll talk a little bit later about the calculations for density. But then it is put into the high pressure system, sealed up, and the analysis continues, either up to 33,000 pounds per square inch, which is 227 megapascals, or up to 60,000 pounds per square inch, which is 414 megapascals, depending on which instrument you have. Speaking of that, there are 4 instruments in the AutoPore 5 series. 2 of them have 4 low pressure ports, as we see here, and 2 high pressure ports, as we see here. The other 2 only have 2 low pressure ports and 1 high pressure port. Now, for the ones with 4 and 2, one of those goes to 33,000 pounds maximum pressure, or 227 megapascals, while the other one goes to the full 60,000 pounds per square inch, or 414 megapascals. The same for the unit that only has 2 and 1 configuration, a 60,000 psi maximum or a 33,000 psi maximum. So the AutoPore, as I said, there are 4 models in the AutoPore 5 series. This is kind of a continuation from the 2 previous generations of AutoPores, which had the same configuration of instruments. What makes the new AutoPore 5 significantly different there than its predecessors? There is updated software, which we will take a look at shortly, but also there's updated hardware, and particularly the electronics have been brought up to the state of the art. But there's a number of new safety enhancements that have been added to the new AutoPore systems, to the AutoPore 5. One of those, I mentioned that we evacuate the sample. Since we're evacuating a system that previously had mercury in it, there's no mercury, significant amount of mercury in it, and there's just a little residue in there when we're evacuating sample. On the vacuum pump housed in the bottom part of the instrument, there is a sorption filter that will trap any mercury vapors that might happen to make its way through the vacuum pump. Speaking of mercury, we have to get mercury into the system. We have a reservoir inside. It is located here for mercury inside. We set the bottle of mercury here. It's very convenient and very easy to tilt that bottle to get the mercury to go in there, because the bottle has some mass to it. So we want to make sure that we can easily pour the mercury in there without the risk of spillage. Now, if you do happen to spill a drop or two, you can basically just push that drop into this little machined recess here. We can put a little thin layer of oil inside there, maybe the oil that's used in the high pressure system, and that way it prevents air coming into contact with a mercury droplet, and if air can't come into contact with a droplet, it can evaporate. And then when you have time, you can, when it's at your convenience, just evacuate that little bit of mercury out of there. Now, mention this barrier. This barrier being, besides being impermeable and acting as a spill barrier, it is also a thermal barrier. It extends all the way back to the back of the instrument. A part of the safety features is that we keep all of the heated components, those that produce heat, like motors and power supplies and the vacuum pump, in the lower portion of the instrument. We keep the mercury reservoir, which is our supply of mercury during the analysis, and we move bulk mercury up into the low pressure ports, always under vacuum. We never pressurize the mercury as we're moving it. We move it only under vacuum. But we keep the mercury in the top part of the instrument away from those heat-producing components. There are fans inside to help pull the heat out of the instrument. So again, we want to keep the temperatures around the mercury constant. We want to keep them about room temperature so that all the heat-producing devices are in the bottom. Speaking of temperatures, at the back of port number 2, and again, port 2 is along the central axis of the instrument, we have a temperature sensor mounted. It serves 2 purposes. One, it can monitor temperature inside the instrument. And if that temperature rises above a threshold that the operator can set, it'll warn the operator. A message will appear on the screen saying, hey, it's getting warm inside the cabinet. Again, when working with mercury, we want to keep temperatures down because we want to slow evaporation of any mercury that happens to get loose and get stray from us. We also use that temperature sensor to determine the density of mercury that is surrounding the sample when we fill it, and that helps us in getting our bulk densities, as we'll explain in the software in just a few minutes. Another thing about the mercury is we do have a little spill catcher trays here. These trays are mounted below the low pressure port, since that's when we're filling with mercury. We do want to make sure that, if somehow mercury, maybe we didn't seal the penetrometer properly, if mercury got out, when we take this out, that's going to be caught in this tray. We're not going to, it's not going to drop down to our surface here. So all of these things are designed to help keep mercury in the system where it is supposed to be, keep it away from you, keep it from getting hot. If you do have a little bit of mercury, there's actually stored inside here when you purchase the instrument a mercury sniffer, a manually operated handheld mercury sniffer. You put a tube in it, you pump it a few times according to the instructions, and it will register if there's mercury, significant mercury vapor in the atmosphere. So all designed with safety in mind. Okay, speaking of sample holders, we do have 19 standard penetrometer configurations for samples of different types and different sizes with different porosities. Now, some of the sample holders, and this one has a bowl volume, a cup volume here, of 5 cubic centimeters. And you'll notice that it can hold a large monolith type sample because it's a nice open cylinder inside there. This one happens to have a very small stem volume so that if our sample's not very porous, we'll still use a significant amount of the mercury available. The mercury available for the analysis is what is inside this metal clad area. And we talk about the software. I'll talk a little bit more about capacitance detections. We have a cap that goes on top and a threaded closure to seal it with. We do put a small amount of vacuum grease in there. When we seal it, I didn't put it on here. I don't want it all over my fingers. But anyway, that's one of the sample holders. That's a 5 cubic centimeter solid. If we're working with powders, we don't want the powders to be aspirated during our evacuation process. So working with the powders, and this one has a 3 cubic centimeter volume, you'll see this little stem is extending past the capillary here. And that's so that we can load the powder in the bottom down here. Evacuation takes place up here, and it helps to keep sample from being aspirated. This one has a larger stem capacity than the one here did. So if we have a sample that is that's small in size but has significant pore volume, we've got a little more mercury to use for the analysis. And then finally, this is a 15 cubic centimeter one. All of these come as both solid and powder type pens. This one happens to be a powder again, with a much larger capacity here. So again, we have penetrometers to meet the size needs, to meet the porosity needs of a variety of samples. Now, to the instrument, it really doesn't matter. We have to give them some information about the volume of the penetrometer when it's empty, and information about which of the stem capacities we're using so that it can convert capacitance into volume. But otherwise, they all work pretty much the same, and they're all loaded pretty much the same into the instrument. So we have these spacers that go around the penetrometers to help hold them in place when we put them inside the instrument. We only use these in the low pressure section. So I want to place this in the instrument, show you how we load the sample. So I'm just going to take this off. This contains electronics to help in that capacitance measurement I was mentioning. You'll notice this safety shield. This holds the penetrometer in there. Even if you take this cap off to look at it sometime maybe in the mercury filling process, the penetrometer is held in place firmly and you just happen to be able to see through it. You'll notice this filler rod here. All of these will have rods in them if I'm only going to do one analysis because I have to analyze one sample because I have to be able to seal the system under vacuum and under pressure. So when a penetrometer is not one of these ports, you need this filler rod in place. The software can sense its presence, by the way. If you have an open port, it won't let you start a low pressure analysis because it knows you won't be able to evacuate. So we'll just take that out. We'll place this in. We'll put the safety cover over it. We'll put the capacitance detector back in place, and we'll tighten it to get it ready for our low pressure analysis. And the software does the rest. So I just wanted to take a few minutes just to kind of give you a brief introduction to the sample holders we use, to the AutoPore, tell you what's special about the AutoPore 5, and we'll continue on now with the webinar. Okay, let's take a quick look at how the AutoPore operates, the technique behind Mercury Intrusion Porosimetry, and then we're going to take a quick look at some of the software features as well. So, Mercury Intrusion Porosimetry, we determine pore size distribution based upon work required to force a non-wetting liquid into open capillary pores. Now, The larger the pore, the easier it is to get the mercury to expand into that, because we are creating surface area of the mercury, so we're fighting against the mercury surface tension. So the larger pores are going to fill at lower pressures, smaller pores filling at higher pressures. We can determine the pressures at which they're being filled with the use of a pressure transducer. Determining the amount of mercury, the volume of mercury intruding into the pores, is a little bit tricky at first, or it could be. We want to do it without any direct contact with the mercury, so we're going to do it electrically, and we'll explain how we use capacitance to determine the amount of mercury that has moved into the pores. This analysis only requires readily available physical constants as parameters, as we'll see when we look at the calculations for determining pore size distribution from the combination of pressure being measured and capacitance measurements. Here we see a droplet of mercury sitting over an open pore, and we see the definition of the contact angle. We see that the contact angle basically is measured below the sample, where the mercury where it's in contact with the sample, and then the leading edge of the mercury. So contact angles for non-wetting liquids are greater than 90 degrees. Now the use of this contact angle we see here in what's known as the Washburn equation. Here we see the cosine of the contact angle being used in the calculation to determine the diameter of the pores being filled from the pressure that's being applied, also with the use of the surface tension of mercury. That is, it's a well-known value. We just need to make sure that we use the correct value of surface tension for the analysis temperature. There is a conversion factor that's thrown in there just to keep all the units in the right form, but depending on the common units that we're using for the parameters going into the equation, so it returns an answer to us, in this case in micrometers. Now, earlier I showed you some examples of penetrometers. Here we see the schematic of a penetrometer, because I want to talk a little bit about how we do in fact determine the intrusion volume that's taking place. We see here the penetrometer with a cutaway section on the capillary stem. We've actually cut a section away here so you can see the mercury that's inside filling the stem. We see the sample actually floating in the mercury, because usually the sample has a lower density than the mercury. Sitting here, this gray bit's our sample. We have not really started applying much pressure yet, so we haven't pushed mercury into the pores of it at this point. By the way, if we know the volume of this sample holder when it is empty, and we can determine that by weighing the amount of mercury that it'll hold, if we know the density of the mercury that's in there. If we know that empty capacity, and then we put the sample in here, we surround the sample with mercury at the point where we just fill the penetrometer, we can determine the mass of that mercury by just weighing the assembled penetrometer plus sample in mercury. And again, we then can calculate the volume of the sample, volume of mercury being displaced by the sample, and get a bulk density. I mentioned earlier that we could determine densities. This is how we do it. And if we then, at the end of the analysis, when we filled all the open pores with mercury, we can calculate an apparent skeletal density by correcting the bulk volume for the total intrusion volume of this sample. So the way we determine the volume intruded, as we apply pressure, up here shown in blue, as we apply pressure, we will push some of the mercury into the pores, and some of the mercury then will move from this capillary stem into the bowl, into the sample. The glass I showed in the when we looked at the penetrometers, the outside glass of this stem area is coated with a metal, and we can tie that to the ground of the instrument, and then we can attach a capacitance circuit to this metal cap that seals the penetrometer. So now we have a capacitor that varies in length as the mercury moves down the penetrometer into the sample. So if we just simply measure the capacitance values without making contact with the mercury, we can then determine the amount of mercury that's moved in there. Now we do this because we know a penetrometer constant. That's a value that will convert change in capacitance to quantity of mercury. So we take an original first capacitance measurement, and then for each data point, that's basically zero intrusion, and then for each data point, we just measure the capacitance as well as the pressure to calculate the pore size distribution. Now, I showed you that the instrument consists of both a lower pressure portion on the top and a high pressure portion in the bottom. We do match together those data that are collected by those so that we get a smooth transition between the low and the high pressure. And if you recall, I showed you that the penetrometers have different diameters for that capillary region. Each one of those capillary diameters has a slightly different penetrometer constant. And we simply just enter that when we're setting up the software analysis. Speaking of the software now, let's pause a little bit from this presentation, and I want to take you over and just highlight some of the features in the software. I have an example of an analysis of a separator sample that we can look at. So here we see an analysis of a separator. This was an analysis where we started at a low pressure, less than 1 atmosphere, a subambient pressure, and with filling of the porosity as we go along. Now, one of the things that we noticed from this is showing us that the porosity is a value of about 90% here. That's a little bit high. And also we're seeing some very, very large pore sizes here, up to several hundred micrometers. Now, what we know about separators is they tend to have pores that are in the size of nanometer range, or less than 1 micrometer, and porosities are more on the 40 to 60% range. Well, because of the thin morphology of these separators, they're about a few micrometers thick, we actually have to stack several of them in the sample holder in order to get a reasonable representative sample in there and a significant enough amount of mercury being intruded. So what we're seeing here in the left-hand side of these graphs, we're seeing the filling of the gaps between those spaces. Now, this is an example of our microactive software for the AutoPore, and one of its nice features is after the analysis is over, we open the sample file, it comes up and it shows us the data here, and I can take and move this blue bar here, I can grab it and start to slide it over, and I can actually edit the data. And if I take this over to where, if you look on this lower right-hand graph, it's showing pressure in megapascals. If I take this over to about 1/2 megapascal, which is going to correspond to a pore size of about 2 micrometers. So, and let's just take off the extrusion here so we see a little better. So here we see what is probably the pore size distribution actually of the pores being filled. We've removed that interstitial filling. And now we do in fact see, if we just change our density value to this to be calculated, our bulk density to be calculated at the same corresponding value, we see now about 50% for the porosity, and we see here that our median pore size is about 130 nanometers, much closer to what we would expect for a separator plate than what we saw earlier when we included the interstitial filling. So it's just one of the features of the microactive. It's very easy at the end of the analysis to go back and to make corrections to the data if you need to because of the morphology of the material. Now, one other thing I just want to show very quickly, we can see the instrument schematics here during an analysis while it's taking place. Here we see the low pressure portion on the left-hand side. Remember, we've talked about having 4 data ports, 4 analysis ports that we can add sample to, and then the high pressure system over here with its 2 high pressure chambers. And as I mentioned when we were just talking about the hardware, it's like 2 instruments in 1 cabinet, because other than power connection and other than the digital I/O boards and so forth like that direct the data to the computer, they really are separate systems. So anyway, we want to get back now, kind of close this out. I want to thank you for my part of the presentation. Jeff's got a little bit of a closing here he wants to give, and then we look forward to talking to you later. Thank you.
Thank you, Tony. Today we talked about how the AutoPore could be used to analyze the separator. And the separator is a very important part of safety of the battery. But other important parts of the battery are the energy density as well as the cycle life. And Micromeritics equipment plays a key role in helping optimize those properties. For example, density, surface area, particle size, as well as powder flow can help to improve those. In the battery electrode manufacturing process, it can help with the quality assurance. For your current lithium-ion batteries, it's important for the R&D to help optimize that. And then for next generation batteries, the equipment is key to understanding how to improve and develop that technology. There's many different roadmaps out there of what the next 10 years is going to look like for the battery industry. And we are involved in every aspect of those. This slide shows the different papers over the last 5 years on the different technologies that are being developed. And Micromeritics is being used for solid-state technologies, different types of ions, lithium sulfur, sodium ion, or multivalent ions. As you're going to the anodes, the silicone anodes we're involved with, as well as recycling, and as we talked about today with the separator, ceramics technologies to improve the thermal stability. Thank you for attending our webinar today. If you need more information, please go to our website. Also in the On24 resource section, there's more information. Please stay tuned for questions.
Thank you, Jeff and Tony. I'm opening the chat for everyone's questions, and we already have a few. Tony and Jeff, during your presentation, you showed really nice data on a separator. Some separators are coated with ceramics. How does this affect the end result?
Okay. Obviously, the coating on the ceramic, it may have an impact on the size of the pore openings through there. It depends on the size of the structure or of the separator plate before the coating was added. So you may see changes in the total porosity. You may see changes in the pore size distribution that results from that. But the thing is, the ceramic coating still demonstrates a contact angle with mercury greater than 90 degrees. Mercury doesn't wet the ceramic material. We may have to adjust the contact angle slightly depending on which ceramic is being used. But it's still, you still just as easily can determine pore size distribution and information from coated ceramic, those coated with ceramics as you can with the uncoated separators.
Great. We have a question from someone who has a TriStar, and they're curious if they want to further analyze their separator. Can you do anything special with microactive with something like gas absorption data and mercury porosimetry data?
Sure. If you collect the full isotherm in the physisorption analysis, so you're determining the pore size distribution, physisorption analysis covers a slightly different pore size range than does mercury intrusion porosimetry. And so you can extend the data, use the two together. There's a couple of ways of doing that. One is simply to overlay the distributions within the microactive software. Since the TriStar is a microactive instrument as well as the AutoPore, either software package that comes with the instrument can be used to generate this overlay. You'd simply just import one sample file, or you point to the other sample file. There's something else that's in that. There's a standalone version of the microactive software. It doesn't control instruments. It can be loaded on a separate computer, and it can it can read data from all of the Micromeritics microactive instruments, and that includes a special functionality to create a unified pore structure report where it doesn't just simply overlay the physisorption data and the mercury porosimetry data, but it actually calculates a single pore size distribution using a deconvolution routine from the two separate raw data, the intrusion curve as well as the isotherm. In addition to that, one of the important parameters that's used to calculate the tortuosity factor, which is important for the separator plates, is the BET surface area. So it's nice to have that as well if you're going to look at tortuosity factor from mercury intrusion.
That's great. So having the combined data set actually allows you to get more information than having just interpreting them separately.
Exactly.
Great. Does this require any additional software to do this with microactive?
Well, each of the microactive instruments is fully microactive capable for data of its type. The AutoPore, you can do everything in the AutoPore software there that's connected to the instrument. Everything that I showed with editing the data to edit the analysis range, to remove interstitial filling, for example, can be done right there on the instrument. You can also install a standalone. We offer a standalone version of Microactive that can be installed on any computer, and you simply just transfer the sample information files from all the respective different Micromeritics instruments. That can then, you can do Microactive type post-analysis review of data for any of our Microactive instruments, and it has that special feature of allowing you to calculate a single pore size distribution from a physisorption isotherm and from an autopore intrusion curve. But the TriStar is built-in Microactive for working with physisorption analysis. The autopore has built-in Microactive capabilities for working with the intrusion data. And recall that those two, any of our physisorption instruments and the autopore, you can simply do the overlay of the pore size distributions within them. You don't have to have the standalone Microactive to do that. You just need the data file. But if you want to do the single pore size distribution, the unified reporting, that does require the standalone Microactive.
Thank you. The next question is really a challenging one. Are there any porosimeters designed specifically for in situ battery testing?
I am not aware of any. I mean, if you imagine trying to get inside an operating battery and do some sort of analysis there by mercury intrusion or even by gas absorption, I cannot imagine how you could do that. I mean, everybody always loves to be able to do in situ analysis, but at least these techniques we're talking about today, that's not capable or available.
With respect to the measurement, what's the largest monolith sample that you can fit in one of these cells in the penetrometer?
Good question. Good question. The 15 cubic centimeter penetrometer that I mentioned, the largest one that I showed there, it has an internal depth of about 26 millimeters and an inside diameter of 26 millimeters. So anything that'll fit in a 26 by 26 millimeters right cylinder, you can characterize.
The next question is with respect to the electrodes. Some of these electrodes are sheets of copper or aluminum with a coating of graphite or another active material. How do you measure the porosity of that electrode?
It's another good question, because with using copper plate foils or using aluminum or aluminium, however you pronounce it, foils, those two elements do form amalgams with mercury. But the nice thing is they also carry usually a surface oxidation from being exposed to the atmosphere. And so we can get to reasonably high pressures before the mercury can break through that oxide coating. And so as a result, we can characterize the graphite or whatever the coating is. One of the things you do want to do usually is hopefully you know the mass of the foil itself, and we would subtract that from the sample mass so that the results are normalized to the mass of the coating. But yeah, I mean, we've done these type analyses as well on these copper and aluminum foils.
Thank you. Tony, the next question is with respect to contact angle. With mercury porosimetry, sometimes it's difficult to be very precise about the contact angle of all of these different surfaces. Is there a way to use something like gas adsorption, perhaps, to get a better understanding of what the correct contact angle should be for these systems when we use mercury?
Yes, that's a frequently asked question. Think about it this way: if your pores are in the same size range, if the sample doesn't have pores that are too small to be characterized by mercury intrusion or too large to be characterized by gas absorption, remember I mentioned that overlay. We could overlay the two distributions, and if they don't quite line up, we know quite well that the contact angle between the condensing film of, say, liquid nitrogen or whatever gas we're using for physisorption, it pretty much is zero. There's not much uncertainty there. So the uncertainty is that contact angle that's being used to convert pressure, the mercury intrusion analysis into a pore diameter. We can adjust the contact angle to get a better overlap of those two. And we can also from the mercury intrusion data, if we have the pore volume distribution, we do assume the pores are cylindrical in shape. If we have a pore volume distribution and we know the diameter of these pores, we know the volume in these pores, we can calculate the wall area. We can sum that up to calculate a total pore area by mercury intrusion. We can compare that with something like the DET surface area. And again, if we don't have micropores present, which have high surface area but cannot be characterized by mercury intrusion, then again we can adjust that contact angle to use an effective contact angle that equates the DET surface area to the total pore area calculated from the mercury intrusion pore volume distribution.
Great, thank you. During the presentation, you showed a lot of nice data with respect to intrusion. But with mercury porosimetry, someone asked, we can also collect extrusion data. What type of information about the structure can we get from the extrusion data?
Okay, there's a number of different things that a number of different data reduction techniques that people have come up with in the past or over time. But basically the concept is that the extrusion data is related to the diameter of cavities. Think of it as the rooms in the pore structure, and that the intrusion is related to the throats or the doorways that go into those rooms. So you can get, from the comparison of the intrusion and the extrusion, you can get some idea into the pore structure about the restricted opening nature of the pore throats going into the pore cavities. Some techniques or data reduction technique that you can use is to calculate the ratio of pore cavity to throat, where you simply just basically you run a line across the intrusion extrusion curve and calculate a ratio of the cavity size calculated from the pressure at in the extrusion data to the throat size for a given total cumulative intrusion, the intrusion data given us the throat size, and look at a distribution of the cavity to throat ratio. Another technique that is used, there is a method that was published in the early 1960s in Italy by Reverberi and others, where repeated intrusions and extrusions were performed, basically to fully intrude and fully extrude, and then go back and work your way down the pressure, go back to the highest pressure and work your way back down, doing intrusion extrusion cycles, covering different total pressure ranges to try to get information about the distribution of throat sizes filling into given cavity sizes.
Great. Tony, the next question is really specific. Tony or Jeff, the next question is really specific to potential reactions between mercury and the surface. Will an amalgamation affect the data and the interpretation of the structure?
I mean, most of the material that we're going to be characterizing doesn't form amalgams with mercury, such as the typical materials used in the electrodes and the cathodes and in the separators. Now, there was the question earlier about cathodes coated onto either copper sheet or aluminum sheet. There is some amalgam formation that could happen there. Frequently, just with experience, we've seen that happens at very high pressures that are higher than what is necessary to determine the pore structure of the cathode and of the electrode. So we simply just don't go to those pressures, or if we do, we can use the microactive software again to remove impact of that. One of the things that happens when the amalgam forms is it releases heat. And since mercury used to be used in thermometers all the time because its density changes with temperature, if we look at the intrusion curves carefully, we can actually see typically that heating that's taking place. And it's not a high temperature. It's a small amount of heat generated because it's a small volume of the copper and the aluminum. But we can basically see where that is happening, and we simply just truncate the data there. We don't use data up in that area. mercury intrusion analysis is a destructive technique to the sample because you're never going to get all the mercury off of it, so you're not going to reuse it for anything else. So the fact that an amalgam forms, it's not going to impact something you might try to do later with the sample.
Okay. We're just about out of time this morning, so one final set of questions. Two came in from one attendee. Can we use mercury intrusion to characterize other components like anodes or cathode materials? And then the second piece of that is, what additional suggestions do you have to characterize these components?
I mean, obviously, as we've been mentioning in the last few questions, yeah, we've done characterizations using mercury intrusion of the electrodes and of the cathodes. Some other analyses, and it was in one of the kind of the last slide that Jeff showed, or maybe the one before the last. All the different types of steps in the process where different micromeritics instruments are being used. Particle size distribution of the materials used to make the cathodes. If you get too many fines in there, it can be very, very, it can cause some issues and some problems in the electrode that's formed from that. And our Setograph, we have done quite a bit of characterizations of the powders that are used to make the electrode, because it is very sensitive to the total amount of fines, the total, that are in the sample, and by being able to give reliable information about the mass percent, say less than a micrometer, less than half a micrometer, is very critical information for the material used in the electrodes. We mentioned doing physisorption analysis, for either the electrodes, the electrode powders, or the separators. As far as forming the electrodes, you're looking at powders that are flowing against each other. The Freeman technology, FT4, is very useful in looking at powder rheology of the materials that are used to make these electrodes. There's been quite a bit of work done by Micromeritics and by others with those at Freeman Technology to support the battery market. Density, our AccuPicks that are used for skeletal density, density of the powders that are being used and of the substrates that are being used, as well as the GeoPick for the transaxial pressure density, similar to a tap density but under a controlled application, to look at how these powders are compacting. How does the volume change at different pressures being applied? Not strong pressures, but mild pressures, to see how these are condensing or compacting down, particularly those that are used in the electrodes. So, I mean, there's quite a bit. I could go on and on and on, but there's a lot of steps in the process. One of the things we have, Micromeritics has on its website, and I think there will be a link here, there is an application note for characterization of batteries and things that are going into lithium-ion batteries, and it mentions a lot of these.
Well, thank you. That's all the questions we have time for today. If we haven't been able to get to your questions, one of our application team will be in touch shortly. Tony or Jeff, is there anything else you'd like to mention today?
I just want to thank everyone who took the time today to attend, and obviously there's been some great questions that have come in, and we'd love to get those, and, feel free to reach out if you have additional questions. That's why we're here.
Great. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we'd be grateful if you could complete the survey, which we will be distributing in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again soon. Thank you.